parts. Okay, the rest of chapter 3, we're really going to investigate polynomials more and more. You've already dealt with a few polynomials. You've dealt with linear, you've dealt with quadratics. We looked at what polynomials were back in chapter P, but we might need a quick reminder of what makes a polynomial a polynomial. So let's just read this top part together. We'll look and answer a few of these questions. It says, we introduced polynomial expressions back in chapter P, but we have not discussed them since then as far as what characteristics are involved. So let's quickly review what it means to be a polynomial versus not. Here's some examples. So take a look at the examples of what would make a polynomial and the non-examples off to the side. And based on these above, I'd like you to answer these two questions. A, what must be true of the exponents on the variable for a polynomial? And B, what must be true of the coefficients in front of each variable of a polynomial? Why don't you, with your new partner, discuss these, answer these two questions, and then we'll share the answer as a class. The answer to letter A, what must be true of the exponents on the variables for a polynomial? Catherine. Yes, love it. They have to be whole numbers. Remember, whole numbers are just all the positive, like tick marks on a number line, but including 0. So you could have an exponent of 0, of 1, 2, 3, 4, and above. Nice. Nice job, Catherine and Katie. Letter B, what must be true of the coefficients in front of each variable of a polynomial? Jaden. Yes, they have to be real numbers, no imaginary. They could be rational, they could be irrational, but they have to be real numbers. I should put my pen down somewhere. Oh, there it is. Okay. So yes, real numbers. Now, we looked back all the way in chapter P, which was before Christmas break, that you classify polynomials. Really, they have a first name and a last name. The first name is by the degree, which is referenced as the highest exponent in the problem, so the highest exponent on the variable, and then they have a last name. The last name is how many terms you have. Olivia?
Doesn't A have to be positive?
So as a classification of whole numbers, that's all the positive numbers after 0. So it's basically 0 is included if we kind of put our answers in interval notation, 0 to infinity.
Not for the exponents, for the coefficients.
Oh, the coefficients, actually, they can be negative.
Even for A.
Even for A. I know that these examples didn't show any, but an example that I could have added as a polynomial would be y equals negative x squared, and that would be a quadratic facing down. So they can be negative. You're right. That's a good thing that actually, even for next year, I should probably add that you could have a negative exponent. So thank you for clarifying that. Okay, so first name is what the degree is of the polynomial. Second name is how many terms it has. So let's see if we can classify. Example 1. What would be its first name? Out of those lists, A through F, what would be the first name of this polynomial? Raise your hand if you can tell me. Nate?
Quintic.
Quintic. And here you go, Nate. Nice job. And somebody else, raise your hand if you can tell me what would be the last name. Say quintic blank. Jeremiah. Monomial. Perfect. Okay, we did one there. Okay, guys, go ahead and check your answers. Check to see that for example 2, you had cubic trinomial. Example 3, you had constant monomial. Now, one thing to be aware of, this will not be asked of you in your homework. We already had to classify these back in chapter P. It's just a quick reminder. So if the problem in chapter 3 tells you we're working with a quintic trinomial, you know that that's a power of 5 with 3 terms. Or if I start referencing these, just because I'm a little bit more accustomed to these terms, if you need a reminder, just let me know, but I just want to take a moment to review. All right, so let's keep going here. Our goal for today is going to be looking at what makes a polynomial, and what are some of the key characteristics about their graphs. First one here kind of shows you what polynomials, what the curves tend to look like, and what makes a polynomial, or what type of curves would not classify as a polynomial. So it says if you looked in your book on page 292, there are pictures of graphs that are polynomials and pictures of graphs that are not. There is a characteristic that your book does not list, and that is that the domain of all polynomials is negative infinity to infinity. It's all real numbers. Okay, what I did is I copied the image from your book, so you didn't have to go and look into it. But you can see just the type of curves that make a polynomial, and I'd like you to just take a moment and see how you can maybe see this picture in the future and recognize what is the problem in the picture that makes it not a polynomial. So obviously in example 1, it says not the graph of a polynomial. What about, oh, this is weird. Oh, well, that's right. What about this first graph do you think is making it not a polynomial? Yeah, there's a hole here. There's a hole here. Really, if there's a break in the graph, it's not classified as a polynomial. For a polynomial, you're not going to have any cusps, anything that looks like that. So examples of polynomials they're smooth or they're continuous is what we say. Basically, as you travel from left to right on the x-axis from negative infinity to infinity, the graph is described as continuous. I can continue my pencil all the way through and have no breaks, no cusps, no holes. So same for this one too, even though it starts down below, it's smooth, it's continuous, I don't lift my pencil in any way. Okay, I want you as groups, so as your new partners, to start seeing maybe what characteristics do I see of different types of polynomials. So I'd like you to just take out your calculator. And the reason that you are paired up today is so that you can check each other. Because it says, sketch them accurately on the graphs provided. So you're going to check yourself, you and your partner, and say, okay, do we have the exact same features? Do we have it graphed correctly? And then you'll start looking at some observations together. So I'm going to give you guys a few minutes. Go ahead. It might take a while to do A through F, and then we'll regroup after that. Okay. All right, let's regroup. Back. And we're back. So check to just kind of make sure you have the good intercepts, but you had your partner with you, so hopefully you have these graphs fairly accurate. And then what I'd like you to do, first thing we're going to be looking at is what's called end behavior. Basically, the direction that the graph is going as x approaches infinity, so to the right, and as x approaches negative infinity, so to the left, is called the end behavior of the graph. We represent the end behavior simply by drawing arrows. And we do this because when we start graphing polynomials, knowing the end behavior just makes your sketch much quicker. So what I'd like you to do is we're going to look at 5 and 6. First, you're going to discuss with your partner the relationship between the end behavior. So you're just looking at the arrow markings. Does the graph go up and up, down and up? And see if you can have any commonalities with the degree of the polynomial, so the highest exponent. See, are there anything in common between the degree and the way that the graph has the end behavior, so how it behaves at the end of the graph. And then number 6, you're going to discuss with your partner the number in front of the highest power, or in front of the highest degree, is called the leading coefficient. Discuss with your group the relationship between the end behavior and the sign of the leading coefficient. So I'm going to give you a few minutes because I want you guys to determine this on your own and with your partner, and then we'll discuss kind of what our thoughts were and we'll organize this chart together. Okay, so go ahead and do that. Okay, raise your hand if for you and your partner, you feel pretty good about your observations in number 5 and you'd be willing to share what you observed. Madison.
So if the degree is even, like 4 or 6, then it either goes up, that behavior either goes up or down.
Good. It either goes up and up or down and down. And what about if it's odd?
If it's odd, then it goes like up and down.
Nice. Up and down or down and up. Nice job, Madison and Catherine. That's the observation I wanted you guys to get. That's going to help us as we start graphing polynomials quickly. Okay, and then number 6. Can someone, if they feel confident about what they observed in number 6, tell me what does the leading coefficient do in terms of that? Olivia.
So if it's even and it's a positive polynomial or positive degree, then it's up, up.
Good. So positive even degree goes up, up.
If it's even and negative, then it's down, down.
So negative even goes down, down.
If it's negative odd, it goes up, down.
So negative odd degree goes up and then down, and positive odd goes down, up. Perfect. Exactly what I wanted you guys to get. Did we all see that as we were looking through? I know a few groups as I was walking through, that's kind of what they were observing, which is awesome. Now let's kind of just put these observations together in a table, and I'm going to tell you the example that I think of that always helps me remember these types of end behaviors. So first of all, if the leading coefficient is greater than 0, aka meaning if it's positive, specifically if it's an odd degree and it's positive, then we know it's going to go down, up. Here's the example I always think of. I think of y equals x cubed. Is that an odd degree? Does it have a positive leading coefficient? So what does the graph look like? You guys know this, you were just tested on it. It goes down, up. Now the nice thing is as you work into higher powers, like the 5th power, the 7th power, the 9th power, the 11th power, if you have a positive coefficient, the ends of the graph will behave in the same way. Now, if you look at the leading coefficient being less than 0, aka meaning negative, then it goes the opposite way. What equation do you think I think of? Negative x cubed. Because if I think of negative x cubed, I know that means it's just flipped over the x-axis. So the behavior just goes like this. Starts up and goes down. Good stuff. Now, so if you have a negative x to the 5th, a negative x to the 7th, a negative x to the 9th, it will behave in the same way. Okay, let's take a look at even degrees. If the even degree is positive, then we know that the end behavior is going to go up and up. What equation do you think I think of? Y equals x squared. It's the most basic, and it helps me to remember that the ends of the graph, they go up and they go up. Versus if you have a leading coefficient that is negative, you guys saw that that shows that the ends of the graph will go down and down. And what equation do you think I think of to help me remember this? Negative x squared, because we know that that just flips it upside down. Excellent. Okay, that is the first observation I want you guys to see. In fact, that's going to be the first thing you're going to do when you graph polynomials, is just see how will the ends of the graph behave. Okay, let's keep going. The next most important thing that you see is where does the graph cross the x-axis? Now, the place where the graph crosses the x-axis is very important, especially for implications in pre-calculus. Some terms that you might hear, which all mean the same thing. This really threw me off when I was first learning this. These all mean the exact same thing. Roots, zeros, solutions, and x-intercepts are all just names for where the graph crosses the x-axis. They mean the same thing. Now, by looking back at what you did in number 4, I'm going to give you a few moments with your partner. I'd like you to list all the roots of the graphs. So, for example, if we go back to what we did in number 4, what would be the roots or the zeros or the solutions of graph A? What would be the one furthest to the left? -3, so I'd see that it's at -3. What else? 0 and +2. Now it's going to be helpful for you to list it where I had, and I'm sorry that we have to flip pages a little bit. Maybe use your partner to have them write those down on that page, and the other partner to write them down on the previous page. But if you guys could take a few moments to do that, and then we'll check our work and discuss a few observations. Okay?
Yeah, I can turn to the graphs and then you can write them down. So
Yeah.
we got.
Sorry, I'm trying to unrecord this, but I don't know what I'm doing.
-1
What happened?
and +1 for B.
Okay, so you guys just wrote these numbers down. These were your zeros or your roots, which they're also called, for A through F. Now, looking at, this is going to be some new terms. So I want to read this together with you in number 7, and then we'll just start observing things ourselves. Linear factors are factors in which the highest power on just the x is a 1. The number of times a linear factor occurs for a particular polynomial is called the multiplicity. For example, in the equation y equals x plus 1 to the fifth times quantity x minus 1, the two linear factors are x plus 1 and x minus 1. However, the multiplicity for x plus 1 is 5, and you can see that on the exponent. And the multiplicity for x minus 1 is 1. The equations that you guys graphed in A through F from number 4 are listed below in factored form. So you can see letter A has been factored for you. We'll review how to factor on our own in a minute. But for letter A, the same equation that you graphed in A is rewritten as 0.5 x squared times quantity x minus 2 times quantity x plus 3. So if you multiplied all of these factors together, you'd get that same equation that I had you graph with your partner in the beginning. Now, what I'd like you to do, this is going to take a little time, I'm going to give you some time to do this, is to study the graphs. So you're going to be looking at the zero values. Notice in letter A, -3, 0, and 2 shows up here as -3, 0, and 2. So you're going to be looking back at your graphs and studying the zero values, and you're going to see if you can make any generalizations about the x-intercepts and when the multiplicity is even versus the x-intercepts when the multiplicity is odd. So for example, if I look at letter A, and this is why you have your partner, you might be sharing, one be looking at one page, the other looking at the other. But if I look at letter A, x squared, would that be an even multiplicity or odd? Even. X minus 2, would that be an even multiplicity or an odd? Odd, because it's x minus 2 to the first and x plus 3 to the first. So I want to look at the zero values of 0, 2, and -3, and knowing that 0 is an even multiplicity and 2 is an odd multiplicity and -3 was an odd multiplicity, and see, is there any observations I can make from the graph? So if I look back at that graph, and maybe I'd look at it on my partners, I can see -3 was the even linear factor. Or excuse me, no, I would need my partner's paper. Which one was the even? 0. 0 was the even, here's where it occurred. And then -3 and 2 were the odd multiplicities. And I just want to go through every graph and see with my partner, what observations can I make? Okay, take a few minutes. Okay, Jaden, can you tell me what you observed about an even multiplicity versus an odd multiplicity?
So for an even multiplicity, it bounces off the x-axis. It doesn't actually go through. For the odd, it just goes through the x-axis.
Yes, I like that word. It bounces off the x-axis versus the odd multiplicity. Look at this guy. It goes through the x-axis. Now that is a hard one to see. But if I took a look at the factored form of letter C, I know that this zero value is going to have an odd multiplicity because it's going through. And I know that this zero value is going to have an odd multiplicity because it's going through. If I was looking at my partner's paper for letter D, the factored form, I would know that this zero value has an odd multiplicity, this one has an odd multiplicity, this one has an odd multiplicity. So let's see if you guys can answer this. Looking at the factored form, if I didn't have it in front of me, so I'm looking at this page, this zero value, -2, would it have an odd or would it have an even multiplicity? Odd, because it goes through. How about this one? How about this one? Odd, good. Let's take a look at this zero value. Would it be odd or even? Odd, and how about this one? Even, because it bounced. Excellent. So this is what I wanted you to see. Now we're going to bring it all together and see how could this all help us to graph quickly. So when you're explaining this, it says, can you make some generalizations about the x-intercepts and the multiplicity is even? I like the way Jaden said it. It bounces, you could say the graph bounces off the x-axis. And the multiplicity is odd, it goes through the x-axis. Love it. Okay, I want to try one example with you of how can you bring all this together to graph quickly. Let's say that you have this function. I want to make sure I have something factorable. So let's say I have p of x is equal to x cubed minus x squared minus 6x. And the directions are sketch the graph based off of what you know. Well, we just looked at like multiplicities. What form do you think we would have to change this to first? Factored form. So let's think about what we know about factoring. Always take out a what first? Greatest common factor. So what would be the GCF of those three? X, good. And that would leave me with x squared minus x minus 6. We know how to factor this piece from first semester. The last term's negative, so we're going to have different signs, plus and minus. X times x would give me x squared. What times what would give me 6? 3 and 2, and specifically a negative 3 and a positive 2 would add up to be that negative x. Okay, let's put this all together of what we just observed with our partner. If I create a graph, I'm going to do this in blue to show that it's different. This was a positive odd degree. So what is going to be the end behavior if I do arrows? Is it going to go down, up, or up, down? Down, up, because it's positive, so it's going to go down, up. Okay, what are the zero values? What are my zeros? 0, good, 0, 3, and negative 2. So 0, negative 2, and 3. I know it's going to go down, up. So I know that here it's going to go down, here it's going to go up. And now we use our observation about the multiplicity. X is raised to the first power, x plus 2 is to the first power, x minus 3 is to the first power. Those are all even or odd degrees? Odd degrees. So what does that mean is going to happen at each zero value? It's going to go through. So I know I don't know the exact values, but I know it's going to go through, it's going to go through, and it's going to go through. The way to know how far, this is a sketch. If I wanted to know exactly how far, I could plug in like a number in between these two, like -1, and see what really comes out. But for just a sketch, I just want to see what's the shape look like. Okay?